Next on the agenda, we have a triple header, two of whom I believe are in the room, and one is going to come in by Skype. Is that right, guys? Someone shaking their head, yes. That's good. So I will introduce everybody first, I think. Is that fair? Makes good sense. Okay. Dr. Guy Larocque, our research scientist for Canadian Forest Service at Laurentian Forest Centre in Quebec City, an adjunct professor in the Faculty of Natural Resources Management at Lakehead, and the Forest Research Institute at the University of Quebec in Abitibi-Témiscamingue. Guy got his undergraduate and master's degree at Laval and his PhD at the University of British Columbia. He's published papers on forest productivity and succession, carbon cycle, and development of empirical succession and process-based models. He is the editor of Ecological Forest Management Handbook, which was published by the CRC Press. Angus Carr. Angus, would you stand up right back there by the corner? Angus works in the intersection of forestry and GIS. He's been writing decision support tools and analysis for 20 years in both Saskatchewan and Ontario. He presently works for MNRF in Industry Liaison. He has a Master's of Forestry and a Bachelor's degree in Outdoor Rec and Biology from Lakehead University. He feels at home here, I'm sure. And finally, by Skype, Dr. Wayne Bell. For you who don't know Wayne, he leads the Biodiversity and Conservation Research Program at the Ontario Forest Research Institute and is an adjunct faculty member at Lakehead University. Wayne has authored over 100 papers related to forest ecology and silviculture, and in 2015 received his PhD in environmental biology at the University of Guelph. In preparation for his potential retirement in 2021, Wayne says he's starting to study more complex things like mixing cocktails and ballroom dancing. So with that, Dr. Larocque, I give it to you.
Thank you very much. I would like as well to introduce two other members of the project. In fact, the project supported by FST was process-based forest growth modeling using eFRI. And we are making the presentation. Well, I'll get back in a moment, but I would like as well to introduce two other members of the project. Professor Nancy Lucas, she is professor at here at Lakehead University, and Sandra Carr, who is a PhD student. Plan of the presentation, well, I will just give a brief overview of what ZELIX CFS is all about. I will describe, the validation data set, because part of the project was to validate, to evaluate how well ZELIX CFS, which is a succession models, well predicts, the development of forest stands in northwestern Ontario. After the description of the validation set, I will present some results. I will introduce MCMod, which is a modeling software applications. Then Angus will take over with eFRI applications, and Wayne with future opportunities. So, overview of ZELIX CFS. What ZELIX is all about is a succession models, or it is a gap type model. It has a mechanistic basis. It's not a statistical model, in the sense that all the basic processes of tree and stand growth are represented using mechanistic equations. So in the representation of the main processes, we have competition, regeneration, mortality, treefall gaps, and the ecological constraint on growth. And one of the main advantage of ZELIX CFS is that it is well adapted for uneven age mixed forest stands with complex structure, and believe me, in Northern Ontario, there are many uneven age forests with complex structure. If you want to have more information about this type of models, there is a complete chapter on that in my book, Ecological Forest Management Handbook. And this is a basic flow chart of the model. Basically, there are probably 3,000 lines of code or something like that, and that was developed in C, C++. So when you generate the information, when you have all the initial data, including climatic information and so on, then for every step in the simulations, you have the prediction of tree mortality, tree growth. After that, regeneration, update of all the information or the data, and then the cycle keeps on going in a loop. I mentioned that it has a mechanistic basis. It's not a statistical model, so you have site constraint on growth. Available light, for instance, so that means each species has its own light tolerance factor following the curve that you see there. Same thing for temperature. Each species is characterized by its degree days limitations. Minimum degree days within which it can grow, and maximum degree days within which it can grow. And these are computed using annual mean temperature. Same thing for site fertility factor, and same thing for soil moisture. So with the precipitation data, you can effectively generate some soil moisture factor. Initialization data, what you need are, I think there is a laser beam on that. Am I correct?
Could you stand at the podium? We can't catch you.
Oh, okay. Okay, so in the initialization data, what you have are species-specific ecological properties. These are constant. They are given, with the initialization data set. You have monthly mean temperature and precipitation data. You have for each species in your stand germination rate data. Then you have for each species a species code, and as well its DBH, and everything starts from there. For the validation data set, I had 3 validation data set that I used for Northern Ontario. These were American can. After that, I had the Spruce Falls data set, the Spruce Falls pulp and paper data set, the Kimberly-Clark data set. We had 9 species, which were balsam fir, black spruce, white spruce, northern white cedar, white birch. After that, we had jack pine, a very important one, and we had 2 other ones as well, but they were not really that important. So if we look at some results, these are the results for American can only, because I had limitation in time and space as well. This is for balsam fir. And what you see there is that the blue lines are the observation data, and the red lines are for the predictions. And you have the error bars are standard deviations. So as you can see with that, the general pattern well agree with the observations, but there are large overlaps between prediction and observations. Now, why in the observations you have ups and downs? This is something, it's nothing weird with the data set. It is something that sometimes, there is so much variability in terms of regeneration, or seedlings that become trees, and then after that trees that die and so on. So that's why you see that kind of pattern. But again, I will have, you know, the next steps will be to go analyze in more depth, you know, the prediction and observations, and probably make a distinction between the different forest types that you have, or as well between pure stands, mixed stands, and species mixture. But in any case, the general pattern agree. Same thing for black spruce. You know, good. You know, the general pattern is there. There are fluctuation in the observations, but you have large overlaps between observations and predictions. Same pattern for white birch. Same thing for white spruce. Same pattern for jack pine, but you have many more fluctuations than the other species. Tamarack, same thing. Now, the only species that, well, it's funny. The predictions and observation do not agree that well, except by the end of the simulations. Because one thing that I forgot to mention is that the historical data set where we had remeasured data, well, it was for a maximum of 57 years. So there were some stands that were measured for a 57-year period, which is good. So in this case, what happened is that by the end of the observation period, there was a very close match between observation and predictions, but not before. So that species will be more difficult to understand what's happening. So now I would like to make a shot to introduce very briefly what MCMOD is. MCMOD is a modeling software platform that facilitates the development and use of different type of forest models. And and as well, it was developed to facilitate the use of different types of models within a project. So you could have growth model, succession model, population dynamics for wildlife populations. You could even include, and that's what I'm doing right now, a wood property model or a forest management model. So this is, you know, the basic framework of MCMOD, which is there, you know, at the left here, to indicate that you can include many models within a project. You can show the results at different scale, at the tree level, site level, or landscape level. One thing that we have been developing as well, or analytical, or oops, I screwed up. Okay. One thing that we are developing different utilities to facilitate the analysis of simulation results, and that could be uncertainty analysis, sensitivity analysis, optimization, and so on. At some point in time, we are going to develop, we are going to use artificial intelligence routines to generate management scenarios. Now, this is just, you know, the picture of what the application is all about. It's nothing fancy, but it's just to indicate that you may have different models within a project, because you may have, you know, in a workspace, different projects, and within the projects, you may have, you know, as many models as you want. Again, this is, you know, a detailed view of of all the information you can provide the MCMOD with, including the name of the models, the input file, output file, or even intervention files. And again, just to indicate that another utility here to include comments. Now, some of the visualization facilities, you are going to have, for instance, basic graph, line graph, you know, to see the results over time. There is a connection between SVS, so MCMOD, you know, ensure that make the connection between the results and the use of the stand visualization simulator, and as well there is a connection with a geographic information system. So let's say you have a model that makes predictions for several stands within the landscape. For instance, if you want to have 100 stands, within your simulation, then you can also see results, at the landscape level using, the utility for interfacing with a GIS system. In this case, we use Quantum GIS. Just to hear an example of using Quantum GIS, we developed, with the help of Angus originally, an application to show results using pie charts. So here what you can see over time the change, for instance, in species of proportions or any other indicator that you would like to see. And that's it for me, so Angus. Be careful with the button here. It's confusing.
Okay, where are we here? Can you actually hear me? Okay, good. So where I got involved in this project was trying to tie in eFRI data with modeling it, and it's kind of a pain in the arse. So, because really what you need to do to run a process-based growth model, he was mentioning you need to tie in the climate, you need a tree list, and none of which we have in eFRI. So how do you get from eFRI, doing something in the model the landscape model you actually have, to doing this process-based modeling? And gathering that data and turning it into something you can use, you're not going to do it if all you're trying to do is some simple forestry stuff. So that's where I got involved. So eFRI is modeling input. So is climate, so is growth parameters, etc. So how do we extend from that site-based to a broader landscape level? We do it several times. How do we get there? Well, you need some assistance software, because although it's not terribly conceptually difficult, you're not going to do it if it's hard to do. So we start with the stand label, species, comp, age, height, stocking, and invent a tree list for process-based modeling. Because, well, that's what we got to do. How do we get there? So, well, first of all, site index. We forgot to do it in all the eFRIs. Darn. Now, Garnet will tell you he's got some great routines. Again, tying into those, you got to start somewhere, you got to build it, you got to go somewhere. And so we're not there yet. So stocking, did we do stocking? Can we use stocking? Anyone? Sadly, we did crown closure and didn't estimate stocking in all of our eFRI. So what do we do? Well, Wojtek came up with some equations, right? So we can plug in the equations somewhere in this. So we should be good, right? Yeah, I keep saying that. So we've got crown closure, we can estimate stocking, we should be good. They're not really insurmountable difficulties. They make you wonder about your data? Sure, absolutely. And that's up to you doing something with it. That's okay. So, big flow chart. This is lots of balloons. So really what we did was we started off with your eFRI stand label. Somewhere in here there's the laser pointer. I'll probably hit the wrong button here in a minute. Is it that one? The red one, hey, yeah. So we start off with our stand label, think about crown closure and what to do with it. And where do we go from there? We take our species comp, height, and age, and well, let's see, we can estimate some basal area index, see how we're doing. We can take it into some Polanski tables, coming off Pandy and Wang, 96. Yeah, we're not using MIST in this. We're not up to date, I know. That's because this is, Plonsky's still simple and easy and we all understand it, or I do anyway, maybe I'm showing my age. But also the calibration plots for eFRI use it. That's why we're using it. So we're using it. We're using Plonsky still. We'll come back to that as we move forward a generation and we can actually do something resembling stocking from MIST. Then in the field. Once we get there, then we can talk. I'm not ready to move yet. So, calculated stand density. We adjust the species comp based on stocking. Okay, so get there. And come up with a number of trees. Fundamentally, we're going through Plonsky and estimating this number of trees in a plot. Then we'll go through, generate some random locations for them, assign some species, assign a DBH from Plonsky. Ideally, we'd like to use some DBH variability because that would help in the process-based modeling, but at this point, I couldn't get it through my head. I admit it. So, still got to read that paper a few more times. But right now it's generating, yeah, flat, they're all the same. But we'll get there. So we come up with synthetic plot. This one, for example, we have a whole schwack of trees. I like rectangular plots. They're easy to tell if you're in or out. So these are all in. You'll notice these little red stars along the way. Those are the stations for an eFRI cruise. The only way I'm going to compare a calibration plot against a synthetic plot is by cruising it, in quotes, right? So cruising that, you should be able to do a prism sweep around each of these points and say, hey, I did exactly what they did in the field, except in the computer. So this was my theory about how we would evaluate this. I got shot down a little bit by the calibration plots, by the way, but we'll come back to that. So I worked up a Python script to do this work, and if you actually want to use it, you'll find it in QGIS. You could quite easily rig together an interface in almost anything, frankly. I just did it in QGIS. But the internal modules of it are all usable in anything. All they do is they're classes. You call them, you get data back. So, and you can just install it from the QGIS plugin manager. And the code's all on GitHub anyway. Well, GitLab, sorry. So, a dialog box. I'm not going to explain it. Oh, he left. Okay. I'm not going to explain it because it's fairly simple. There's where we're getting our data from, you know, some labeling stuff, the size of the plot. We packaged in some climate data because, oh, darn, I don't want to be a climate expert if I'm just doing some simple process-based modeling and playing with the tool. So here, let's toss in some data. So I did some simple climate stuff for Ontario and put it in there. You can do it from a selection, etc. And that's about all you really need to drive this. If you want to use your own climate data, you can. If you want to specify some other details, there's an advanced tab. You can actually do your own calculations for stocking if you want, if you don't have it in the table. So you can calculate it live, whatever. Those are fundamentally to let you play with it and explore, because that's how I would like to use it. I admit it, this is software for me to play with this, so I can play. So, a single stand. This is Jack Pine 100, Site Class 1, Age 100, pulled straight out of a line in Plonsky, okay? It should have a basal area of 27. Now, if you look at this, this is however many hundred samples, 1,000 actually. It's 1,000 plus or minus. Some of them crashed. 1,000 samples from a simulated plot. So what happened? Well, if the normal basal area is 27, why are they going up and down? This is purely the spatial variability of where those trees are randomly placed when you do a cruise. It better darn well be bell-shaped because it's purely drawn from random. But what's interesting is, you know that plus or minus 10% on the check cruises? 27. Wow, we go down there and we go up here. Those are 2 standard deviations, by the way. So that puts us neatly. The random variability of tree locations generates more than 10% on a plot, which I'm entertained by. So from going back in the day when I actually did this, and I was wrong because I was off by 10%, now I can say nana nana boo boo. There's still a child in me, what can I say? Fundamentally though, what the random generation of stuff with parameters coming from Plonsky does is roughly what Plonsky does. So, okay, the approach isn't awful. And I've got some more stats on that somewhere else, but the approach isn't awful. What happens when you do it on an actual stand, real stands? So what I did was I took the calibration plots from eFRI over whatever forests we have loaded, 12 of them, I think. So there's 2,800 plots. Took the stand label, took it apart, corrected it. There's a lot of data cleanup in that data set. Anyway, I'll whine about data cleanup another time. And then took the calibration plots, basal area, and ran it through the simulator. Because, well, what the heck. So if I looked at the error, now this looks awfully clean. I'll tell you about the colors in a moment. This looks awfully clean because I actually had to go back to this and say, okay, I'm just doing the fully stocked stands. That's why there's 2,700. There's actually about 5,000 in the data set, and I threw out everything that wasn't close to fully stocked because otherwise it didn't make a nice pretty graph. Let's face it. So the reason for this is there's some really wacky stuff in there, and I just wanted to look at something that I could comprehend. So I started off with just the comprehensible. So these are normally stocked stands, 0.9 to 1.1, close enough. So if you take the calibration plot as they actually measured it and compare it to a simulation based off the stand label, age, and height, there's my error centered around 0 and doesn't go up or down too far. So that's not bad. I'm reasonably happy with that. Could it be better? Yeah, it could be tighter. Kind of curious what else I could do with it. But so conceptually, can we get from eFRI to tree lists for process-based model? Generally, yes. There's some details. We definitely need to land that stocking and understand how stocking is really used. We definitely need to use the same stocking measurement in our calibration plots as we use in simulations. So that's why I'm on Plonsky, right? Stocking is still in use. We have to acknowledge that. We can't throw it out. Or we can throw it out, but we have to replace it with something that is used oddly like stocking, okay? We have to have an expression of stem density. Just, you have to. So, ultimately, DBH variability is probably the most relevant thing in this as future work within this context. Nailing that so you can identify in the process-based model which trees are going to die sooner because they're the ones that aren't working out so well. That would be good. The other one I'm personally most interested is the integration into landscape level modeling. I'd like to take the process-based model, take it out to the landscape, run it a gazillion times, and see how the landscape changes in ways that we didn't expect and were outside the climate envelope of what we had before. That's what I'm interested in. So that's my really short section. Do you guys have Wayne on the line?
Yep, should be here.
Okay, you're on, Wayne, and I'm gonna run your slides, but these guys are gonna turn my sound off for me.
So starting with future opportunities, I think what we need to do is use both our ecological theory. There we go. Now I can see it. Ecological theory, and that's to help us with dealing with many issues. But for today, we're just going to talk about forest productivity and the management of species at risk. So next slide. Key thing here, I think if we start to look at our biomes and start to understand how things like climate are gonna look at them, we can go back to Whittaker's work from the 1970s and look at how our forests are lined up with temperature and moisture. I think this diagram of how biomes are depicted in terms of where the taiga, which is the boreal forest, and the northern tolerant hardwood forests are located. Those dark green on the middle right part of the diagram. We can use that information to help us move forward. Next slide. There's been a lot of discussion around climate change. This should not excite us in the least. We've known about the hothouse theory since basically the 1800s, 1905. So well over 100 years ago, it was predicted with a fair degree of accuracy that as we increased CO2 in the atmosphere, we would get a rise in temperature, which we are observing today. I think a lot of the uncertainty around this, though, is not so much what happens if we put greenhouse gases in the environment, but what happens in the political side and where countries like China, US, European countries, in particular, how they react and whether or not they stop burning coal or fossil fuels. So a lot of what the International Panel on Climate Change has probably proposed in those models has to do with our inability to predict the political scenarios and not so much related to what will happen if we put greenhouse gases into the environment. So the uncertainty here is we really can't model political decisions. We don't know 20 years from now what those major countries are going to be doing. So we do need to look at the range of variability that could happen and build models that include that range. Okay, next slide. Oh, my video. If we start to look at ecological theory in terms of how forest succession is going to occur, this is a depiction that I made a few years ago based on some of the information from Sweden. And that on the bottom, we see that we have the pine cohort. There literally is no succession going on there. It's a pine replacement series that every time there's a fire, 80 to 100 years, you cycle back to pine. There's literally no succession occurring there. In the middle, the bluish areas where we have the mixed woods and so into the temperate conifers, we do have succession, and the disturbances occur at say 120 to 350 years cycle for the fire, but we tend to go back, stand replacing back to the beginning, and we do have intolerant species start and succeed back to the mid-tolerant species by the end of a rotation. And then in the pinker area at the top, the gap phase dynamics, where we're managing hardwoods, northern temperate maples, we can't have an area that has no succession again. It's maples replaced by maples, so self-replacing maple stand. So next slide. If we start to look at back to our biome diagram there, and the highlighted yellow lines with the temperature being the main thing that most people are looking at with climate change, and looking at 4 to 6 degrees differences and changing, particular increasing, would put a lot of the taiga biomes that we have today into temperate deciduous or into more grasslands, brushy grasslands. The other factor, though, is you really need to look at what happens with precipitation. And right now, the climate change people really don't have a handle on the precipitation part. So again, back to that uncertainty, if we're going to look at shifts in biomes from the taiga and northern temperate, we really need to get a handle on what happens with changes in moisture. It's not just about changes in temperature. And so in any future modeling that we need to do, we need to consider both the temperature and possible changes in precipitation to predict shifts in our biomes. So next slide. So I'll be working with the group, Guy, Angus, Madhav Sharma, and a few other people to bring together those three conceptual ideas. One, the biomes and the shifts and where those biome shifts may occur. The uncertainty around the politics in terms of how various countries might deal with the use of fossil fuels. So look at the IPCC models and build those in. And then from that, figure out, we'll have to work with fire model people to figure out how our future forest succession and future productivity may look. So it may sound simple, but I think it's going to take a little while to put this together. Okay, next slide. We're also on the forest productivity side. The species at risk side, we're looking at that as well. The target species to begin is caribou. But to begin with the caribou, we need to look at multiple other theories. The first one's the theory of insular biogeography. And we know that we are fragmenting our forests. There's plenty of evidence published both for Ontario and many of the other provinces of how road networks and other things that we do, human activities do, we will fragment our forests. The picture on the right is from central Manitoba, just north of Riding Mountain National Park. We've got the ducks, the porcupines, and the Pasquay Hills. We are considering working with Mark Johnson from the Saskatchewan Research Council on a project where we're looking at the effects of climate change and forest fragmentation on populations, including caribou, under a federal proposal that we're just putting together. And in that, we'll also work with Guy Larocque and the partners from Quebec to look at bringing in the population and community dynamics theories to look at how caribou movement across such a landscape might occur. Next slide. So as species like caribou, and it could be woodland turtles or other species that do move on the landscape, we can look at some of the models that are being developed in Europe at the time. The model on the right of the diagram here depicts where there are impact zones, which are where the populations would be reduced through human activity, whether that's collisions with large trucks, or whether it's more deliberate hunting of the species. But we can look at where those hotspots might be on those landscapes and figure out how to manage the landscape to avoid setting up areas that would lead to these large impact zones. So more using the meta population, meta community dynamics to help reduce the zones, the yellow zones, or the impact zones on such a landscape. Okay, and next slide. So when we bring all that together, I think we'll be looking at a few proposals into the MNRF, climate change folks. We'll be looking at proposals into NSERC strategic grants, or not an NSERC strategic, but an NSERC discovery grant, and possibly two of those, and also the Canadian Forest Service possibility as grants. So when we bring it all together, we'll look at what we know about the biomes, well, what we know about the climate change, what we know about forest succession, what we know about the populations and metapopulations of species such as caribou, what we know about the movement of such species, and what we know about fragmentation's impacts on insular biogeography, and bring all those together into a landscape level analysis using what we have from the work that Guy and Angus have just presented to you. Okay, so that's where I see the future of the project going, and Guy and Angus can be free to add more details there. But that's all for me. Okay, thank you.
I guess we'll have to call it, thank you very much, Angus. Thank you.